Hello everyone, I hope you are having a wonderful day. My name is Kyle Collins and I will be taking you through my first Physics 2211 lab. In this video I will go through the purpose of this lab, explain Newton's second law, show you the experiment through what we are tracking, a computational model using GlowScript of what occurred in the experiment. Then I will compare the graphs and explain, answer lab questions, and conclude. So why are we doing this lab? We want to see Newton's second law in action. The prompt of the lab is to observe the motion of some object that is moving at the same speed without changing direction. Later I will compare two models, one of my observations by plotting both the observed position versus time, and the other is a predicted model, plotting position versus time. First we need to know who Newton is and what his laws are. Isaac Newton was a famous English scientist known for formulating the laws of motion and gravity. His work laid the foundation for modern physics and mathematics, including the development of calculus. His first law is the law of inertia, which states objects at rest tend to stay at rest, and an object in motion tend to stay in motion, with the same speed and the same direction unless acted upon an external force. The second law, which we will be using today, states the momentum of an object is directly proportional to the net force acting on it and inversely proportional to its mass. And his last law states, for every action there is an equal and opposite reaction. So what his second law really says is that the greater force applied on an object, the more it will accelerate. The greater mass of the object, the less it will accelerate for a given force. We can also look at this as the formula force equals mass times acceleration. More important formulas are the velocity update formula and the position update formula. The velocity update formula describes how the velocity of an object changes when a force is applied to it, while the position update formula is used to calculate the change in an object's position over time when it is subject at a constant velocity. So what are we tracking? I have two demonstrations today, one of a person pushing a car and one of me rolling a ball. I put these videos into the tracker and went frame by frame to get the positions. Note that our initial position is supposed to be 0 meters. So here's a video of the car. We can see the graph sloping up from right to left as it moves across the screen. This is a position versus time graph, and we can see the linear slope, which can tell us that it is moving at a constant speed. This is a video I created with the foam ball, which shows the graph sloping up as well. We can see that the total time is 1.268 by looking at the graph and at the table. We are able to find the initial position by looking at the graph and going to 0 and looking at the x. Then I was able to find the initial velocity by finding the second x on the graph and subtracting it by the first x and divided by 0.017. We got the 0.017 by subtracting 0.017 and 0. Here's our code from the computational model. I had to edit the ball position by inserting the starting position from the previous slide. I also had to change the starting velocity by using what we found earlier. Also for delta t, I changed it to 1/60 seconds because I filmed it in 160 FPS. I also had to change the time and use the velocity update formula and the position update formula to help with the graph. Here are both graphs side by side. The predicted one is the orange, while the data from the rolling ball is blue. Reading this data means there was an outside force that made the ball roll faster than it was supposed to. This means we had error. I could have rolled the ball too hard, wind could have pushed the ball, maybe the surface was slippery, or maybe my tracking was off. All of these factors could have caused the curve to look like that. How would your results change and how would they remain the same if you were to flip the axis? Our graph in the tracker would be sloping downwards instead of how it is, sloping upwards. This could also happen if you rolled the ball back from the right side of the screen to the left. However, none of the math would change. Is it possible for you to say how many pushes and pulls, i.e. how many forces, are added together to give 0 net force in the case that you observed? There is something else that did add the force, but the net force was not 0 in the x direction. In the y direction, it is 0 though. With that, we can conclude that labs can take a lot of work and trial and error, but the joy of everything working at the end is worth it. Thank you for watching.